Hello and welcome to the penultimate video in the unit, video 3 on probability. In this video I'm going to discuss conditional probability and independent events. Okay, so if we have a sample space and two events within that sample space, say A and B, and the probability of B is greater than 0, so not equal to 0, then we define something called the conditional probability. The conditional probability that A will occur, given that B has occurred, is defined by this formula. The probability of A given B, this notation on the left is read that way, this is the probability of the event A, given that B has occurred, is equal to the probability of A and B divided by the probability of B. Now, this is a definition for conditional probability. If you think about drawing a Venn diagram of A and B, this is like you replace the entire sample space by just the space B, and then take the proportion of B where A also occurs, and that is then the probability of A given that B has occurred. Okay, and so we could manipulate this expression for conditional probability a few ways to get some useful formulas. One is if we multiply through by the probability of B, then we have something is called the multiplication rule. The probability of B and A, given here, is equal to the probability of A given B times the probability of B. Once again, this is called the multiplication rule. Okay, so let's look at an example of conditional probabilities. This is an example using some of the events that we looked at in the past video. We'll make the experiment be rolling 2 dice, and the events will be the total of the 2 dice is at most 4, and a second event will be at least 1 3 is rolled. And we want to find the probability of E given that F has occurred. That's the probability that the total is at most 4, given that at least 1 3 has been rolled. Okay, let's look at this example. So I've already written here what we had from the previous case when we looked at this before in the previous video. We have this visual representation of the sample space with the roll on the first dice here and the roll on the second dice here. And then E is this area outlined in black. The probability of E was 1/6. F is the area outlined in red, and the probability of F was 11/36. And we want to find the probability of E given that F has occurred. And so in order to do that, remember the definition of the conditional probability here, we need to find the probability of E and F. So let's locate E and F. So those are all the outcomes that are in both of the events, and there's only 2. There's this one and this one. You either roll 3 and 1 or 1 and 3. So the event, in this case, E and F, is equal to the 2 pairs of rolls where you roll 1 and 3, 1 on the first dice, 3 on the second die, or 3 and 1, 3 on the first die and 1 on the second die. Okay, and so the probability of E and F is 2, because there's 2 outcomes in this event, divided by 36. And so the conditional probability of E given that F has occurred is the probability of E and F divided by the probability of F. And the probability of E and F was 2/36. The probability of F was 11/36. This is 2/36 divided by 11/36. And that is 2/11. And so the probability that E occurs given that F occurs is 2/11. That's the probability that you roll at most a 4, given that one of the rolls is a 3, is 2 out of 11. Okay, so this is an example using conditional probability. Now we're going to discuss the concept of independent events. So 2 events are independent if knowing one has occurred doesn't change the probability of the other occurring. So in particular, we say the events are independent if this formula is satisfied. The probability of A and B is equal to the probability of A, event A, times the probability of B. All right? And so, in other words, the probability of A and B is the product of the individual probabilities. So this is related to the conditional probability, in that the events A and B are independent if the probability that A has occurred given B occurred is equal to the probability of A, and the probability of B given that A has occurred is equal to the probability of B. Right? And so remember, here's the definition of independence, and this we can relate this back to the multiplication rule from a few slides ago. Here is the multiplication rule. So in general, for two events, the probability of A and B is equal to the conditional probability of A, given that B has occurred, times the probability of B. And now if these events are independent, then the probability of A and B is equal to the probability of A times the probability of B. And so what that's saying is that the probability of A and B, or sorry, rather the probability of A given B is equal to the probability of A when they're independent. So this first term in this multiplication is just the probability of A when they're independent. All right, so this is very important, I think, to realize that this rule that the probability of A and B is equal to the probability of A times the probability of B only when A and B are independent events. So what one occurring does not affect the chance of the other occurring. So many events that we consider are naturally independent. So in a lot of the examples that I've been discussing, that we would have naturally independent events. For example, the example we just did, the rolling of two dice, the outcome of the roll of the second die is independent from the outcome of the roll of the first die. So for example, the event of rolling a 1 on the first die would be independent of the event of rolling a 1 on the second die, so on. All right. Let's look at another example. Say we throw two dice and let the event E be the total is an even number, and then consider another event L, which is the total is greater than 7. I want to ask, are these two events independent? So this one is not so clear in advance whether or not they will be independent. Okay, so I have here a visual depiction of the sample space. The sample space is the same as the previous example we looked at where we roll two dice. We haven't changed anything about the sample space. We're just looking at different events now. And so let's consider these two events. So in this case, E is the event where the total is an even number. So I'm going to circle using this black pen all the outcomes that would be in that event. There's sort of these diagonals where the total is an even number. All right, so this would be all the events I've just circled where the numbers on the two die add up to an even number. All right, and so that is the event E. And what is the probability of E? Well, we would have to count the number of outcomes that are in that event. Well, one way to do this quickly for this one is to notice that in each row there's exactly 3 outcomes that are circled. And so that means half of the outcomes are circled because in each row there's 3, and that's half of them. All right, so that means that the probability is 1/2. There would be 18 total outcomes in this event out of the 36 possible because there's 3 in each row. Okay, now let's consider the other event. The total is greater than 7. Okay, and so we roll 6 on one of the dice. Then on the other dice we have to roll at least 2 in order to get greater than 7. And so that means this event would be here. And so I include all of these outcomes that I've just outlined in red. L. Okay, and in order to determine the probability of that event, the total being greater than 7, we would have to count the number of outcomes in L. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 out of 36 total outcomes for the probability of L. If we want, we can reduce this fraction to 5 out of 12. The probability of getting a total greater than 7 is 5/12. All right, now we want to determine if these two events are independent. And let's go back and remember what the definition of independence was. The two events are independent if the probability that they both occur, that's E and L, is equal to the product of the probabilities that the individual events occur. And so in order to check this, we also need to determine the probability of E and L. So that E and L is the set of all outcomes that are in both of the events. So these ones, and these ones. And so we can calculate the probability of E and L by calculating all those outcomes that are in both. Probability of E and L. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 36, or 1/4. The probability of E and L. All right, and so is this equal to the probability of E times the probability of L? The probability of E times the probability of L is 1/2 times 5/12. It would be 5/24, and that's not equal to 1/4. And so because the probability of E and L is not equal to the probability of E times the probability of L, these two events are not independent. And that answers the question. All right, so it is important to keep in mind that we can only use this multiplication rule that the probability of E and L is equal to the probability of E times the probability of L if the events are independent. In general, the rule is the multiplication rule I did at the beginning, I put up at the beginning. The probability of E and L is equal to the probability of E given that L has occurred times the probability of L. Okay, so let's continue. And we'll look at a few more examples of this conditional probability and independence by considering some experiments where not all of the outcomes are equally likely. So far we've considered examples where all the outcomes are equally likely. So the die is fair, there's an equal chance of rolling any number. Let's look at some examples where that's not true. So suppose we flip two coins, one we call coin A, another we call coin B, and coin B is weighted so that heads is twice as likely to occur as tails. We want to figure out then what is the probability that both tosses are the same, that is they're both heads or they're both tails. Okay, so let's consider this example. So the sample space is just the same as if we would flip two fair coins, just the set of all the possible outcomes. Heads, heads. So the first of these will be the outcome, the flip that we get when we flip coin A, and the second is the one for coin B. Heads, tails, tails, heads, tails, tails. So there's 4 possible outcomes. If they were fair coins, then each of these would be equally likely, but they're not fair coins, and so we need to figure out what is the probability of each of these. And so let's consider some events. So the first event I'm going to label is H with a subscript A, which will be that we flip heads when we flip A. So on the coin A, we get heads. So heads on A. And so as a subset of the sample space, that's the flips or the outcomes H, heads on both, or HT, heads and then tails. Right? And then similarly, we can have tails on A, and then we'll also define heads on B. Sorry. Heads on B, and tails on B. All right, and let's consider what would be the probability of each one of these 4 events. Okay, so each one of these events is some subset of the sample space. And tails on A would be tails, heads, and then tails, tails, and you can write out, if you would like, the other events as subsets of the sample space. So the probability of heads on A or tails on A has got to be 1, because that is the entire sample space. Now, heads on A and tails on A are mutually disjoint events, and so that means that the probability of their union is the sum of the probabilities, meaning that the probability of heads on A plus the probability of tails on A is equal to 1. This is because these are mutually disjoint events. And because heads and tails are equally likely on A, that means that both of these have got to be 1/2, since they're the same. So probability of the heads on A equal to probability of tails on A equal to 1/2, since we're equally likely to get heads on A as tails on A. Okay, so this is the probability of these two events, heads on A and tails on A. That's not really that surprising. I mean, I guess it's what you would expect, 1/2, 50% probability of getting each of them, but we've gone through using the axioms and properties of probability in order to see this. Now, the probability of heads on B or tails on B has got to be equal to 1, for the same reason as before. The event heads on B or tails on B is the entire sample space, so the probability has to be equal to 1, and these are also mutually disjoint, meaning that the probability of heads on B plus the probability of tails on B would have to be equal to 1. And now the probability of heads on B is twice as much as the probability of tails on B. So on that coin, heads is twice as likely as tails. So since probability of heads on B equals 2 times the probability of tails on B, we have that 3 times the probability of tails on B equals 1. So the probability of the event that we get tails on B is equal to 1/3. And from this equation, then the probability that we get heads on B would have to be 2/3. All right, and so now we've figured out all the probabilities of these events, heads on A, tails on A, tails on B, and heads on B. And we can combine these together to determine the probability that we get both flips the same, either heads, heads, or tails, tails. All right, now let's consider that both the event where both flips are the same is where we either get heads on A and heads on B, heads on B, or we get tails on A and tails on B. Okay, so this is the event whose probability we want to determine. Probability of this event, heads on A or heads on B, right, heads on A and heads on B, or tails on A and tails on B. By the way, this first event, heads on A and heads on B, is just the outcome, heads, heads. We can get heads on both. And this is just the outcome, tails, tails. Perhaps it would be simpler to write just those outcomes. So list this event as those two outcomes. And writing this a bit more abstractly to try to prepare us for more complicated examples. So we have here these probability of the union of these two events, and these are mutually disjoint events, and so it's the probability of heads on A and heads on B plus the probability of tails on A and tails on B. Okay, and now we use the fact that the outcomes of the two flips are independent. Right, so because what we get on the flip of the first coin, the coin A, is independent from what we get on the flip of the second coin, doesn't affect what we get. So that means, remember the definition of independence, that this is the probability of getting heads on A times the probability of getting heads on B, plus the probability of getting tails on A times the probability of getting tails on B. And we figured out what these individual probabilities were, right? Remember, for the coin A, they were both 1/2. So this is 1/2. And then for B, well, they're just up here. So the probability of getting heads on B was 2/3. And then probability of getting tails on A was 1/2. And the probability of getting tails on B was 1/3. Right, and so we add all these together, and we get that this is 1/2. All right, so the probability of getting the same outcome on both of the coins, either heads, heads, or tails, tails in this case, is 1/2. Okay, we're going to look at one more example, and in this example, the experiment is still rolling 2 dice, but the chances of rolling each of the numbers on the dice is not all the same. And so we'll look at this case where the dice are unfair, where it's more likely to get certain rolls, and to determine the probability here. Okay, and so as it says in the example there's 2 dice, and we roll a number from 1 to 6 on each of the dice, but the probabilities of rolling each of the numbers on each dice are not equal. And so the sample space is the same as the experiments we've done in the past where we roll 2 dice, but the outcomes are not all equally likely. So let's look at the outcomes of each of the dice separately. And so I'm going to define some events. This is going to be a similar notation to what I used in the last example. Let's say, for example, the event 1 with a subscript 1 is the event where we roll 1 on the first die. And similarly, 2 with a subscript 1 is roll 2 on the first die. And we'll just continue that notation naturally. So 3-1, 4-1, 5-1, and 6-1 are the same. So these are events where we roll one of those numbers, a particular number on the first die. And we want to figure out what is the probability of each of these events. Okay, so let's look at what it says in the question. The probability of rolling the numbers 1 to 3 are twice as likely as the numbers 4 to 6. And so, for example, the probability of rolling a 1 on the first die is the same as the probability of rolling a 2 on the first die, the same as the probability of rolling 3 on the first die, and that's equal to 2 times the probability of rolling 4 on the first die, and also equal to 2 times the probability of rolling 5 on the first die, and 2 times the probability of rolling 6 on the first die. Right, so the probability of rolling 1, 2, or 3 on the first die is 2 times the probability of rolling either 4, 5, or 6 on the first die. All right, so we'll use a similar method to the previous example to figure out what these probabilities then would have to be. Right, the probability of the entire sample space is equal to 1. And we have to roll something on the first die, so the entire sample space is the union of all 6 of these events. Probability of rolling 1, 2, 3, 4, 5, or 6 on the first die. And so, because of that, we get the probability of rolling 1, plus the probability of rolling 2 on the first die, plus the probability of rolling 3 on the first die, plus the probability of rolling 4, plus the probability of rolling 5, plus probability of rolling 6. Those all have to sum up to 1. All right, now let's use these equations here in order to solve for, say, the probability of rolling 4 on the first die. All right, so these three terms, probability of rolling 1, 2, or 3, are all 2 times 4. So we replace each of these by 2 times the probability of rolling 4. That's going to become 6 times the probability of rolling 4 on the first die. And then these three terms are all equal to the probability of rolling 4. And so this is 3 times the probability of rolling 4 on the first die. And that has to add up to 1. So the probability of rolling 4 on the first die would have to be 1/9. All right, and that was the same as the probability of rolling 5 or 6. And the probability of rolling 1, 2, or 3 is 2 times that. So probability of rolling 1 is 2/9. And that's the same as the probability of rolling 2 and the probability of rolling 3, all on the first die. All right, so this gives us all the probabilities related to the first die. What are the probabilities of rolling different numbers on the first die? Okay, and so we'll remember that. And now we want to think about the second die. So on the second die, the probability of rolling 6 is 3 times as likely as the probability of rolling any number. And so we can do essentially the same thing with the second die. We have that the probability of rolling 6 on the second die is 3 times as likely as any of the other outcomes. So 3 times as likely as the probability of 3 times the probability of rolling 1 on the second die, 3 times the probability of rolling 2, and equal also to 3 times the probability of rolling 5. All right, so I've used these dots to indicate it's also equal to 3 times the probability of rolling 3 or the probability of rolling 4. All right, and all of these would have to sum up to 1, just like before, because the probability of the entire sample space is 1, and these events are mutually disjoint. And so that means we have the probability of rolling 1 on the second die plus 2 plus 3 plus 4 plus 5 plus 6. Those all add up to 1. So each one of these 5 are the same. So the top row there gives us 5 times probability of rolling 1 on the second die. It's those 5. Plus probability of rolling 6 on the second die is 3 times the probability of rolling 1 on the second die. And these have to add to 1. So the probability of rolling 1 on the second die is 1/8. 1/8. Right, and that's the same as the probability of rolling either 2, 3, 4, or 5 on the second die. Let me not write all those down, but just remember that. And then the probability of rolling 6 on the second die is 3 times this, so 3/8. Okay, so these are the probabilities of rolling anything on the second die. Let me just indicate this is a probability of rolling 2. Also the probability of rolling 5, or 3 or 4. Okay, so now we know the probability of all those outcomes of rolling particular values on either one of the dice. And so now let's consider the problem that we're being asked to do. What is the probability of rolling a total of 10 or more? So we need to consider all the outcomes that would give us 10 or more. So let's write that event. Now let's consider the event roll a total of 10 or more. All right, and so let me list all of the outcomes that would be in that event. So if we roll 6 on the first die, we could roll 6 on the second die. We could roll 5 on the second die, roll 6 on the first die. We could also roll 4 on the second die. So these are all the outcomes where we get 10 or more, and we roll 6 on the first die. Then let's consider the ones where we roll 5 on the second die. So we could roll 5 on the first die. We could roll 5 on the first die and 6 on the second die. Could roll 5 on the first die and 5 on the second die. Right? And then we could roll 4 on the first die and 6 on the second die. Right, so this is this event, all the outcomes that are in this event. And we can find the probability of these individual outcomes based on the fact that the two rolls are independent and the probabilities we found for individual rolls on each of the die. So let's consider first this outcome where we get 6 on the first die and 6 on the second die. What's the probability of that outcome? That itself is an event. That's the probability that we roll 6 on the first die and 6 on the second die. Because the two rolls are independent, that's equal to the probability of rolling 6 on the first die times the probability of rolling 6 on the second die. And we got the probability of rolling 6 on the first die was 1/9. The probability of rolling 6 on the second die, well, was 3/8. So here. Okay. And so we just now need to do this for each of the other outcomes in this event, and then add up all those probabilities. The probability of this event, because each of the outcomes are disjoint from the others, will be the sum of the probabilities of each of the individual outcomes. So the probability that we roll 6 on the first and 5 on the second is going to be equal to the probability of 6 on the first, using our notation for these events, times the probability of 5 on the second. And the probability of 6 on the first was, again, 1/9, like in the previous one. The probability of 5 on the second was 1/8. All right. Continue on. Probability of 6 on the first, 4 on the second was, okay, I'm going to skip this intermediate step just to speed things along a little. This is the probability of 6 on the first times the probability of 4 on the second, and that's actually the same as the previous one. 6 on the first was 1/9, 4 on the second was 1/8. All right. Now the probability of rolling the next one, maybe I should keep that here so you can see. Here is the entire event. So we've calculated these three. Now this one, probability of 5 on the first one, 6 on the second one. So 5 on the first one was 1/9. 6 on the second was 3/8. So 1/9 times 3/8. Yeah, the probability of 5 on the first, 5 on the second. That is 1/9 times 1/8. That's probability of 5 on the first times the probability of 5 on the second. Probability of 4 on the first and 6 on the second, this is the last one, is 1/9. Probability of 4 on the first times 3/8, the probability of 6 on the second. Okay, so we figured out the probabilities of all the individual outcomes in this event, and then the probability of the entire event, roll 10 or more, is the sum of all of these. So the probability that we roll 10 or more is what we get when we add up the individual probabilities that we found. And so it's going to be 1/9 times 3/8 plus 1/9 times 1/8. This was the probability of 6 on the first, 6 on the second, 6 on the first, 5 on the second, 6 on the first, 4 on the second, 5 on the first, 6 on the second, 5 on the first, 5 on the second, and then 4 on the first, and 6 on the second. And so let's add all these up. Each of these terms has a denominator of 72, so 1 over 72, 9 times 8. And then we have 3, 4, 5, 8, 9, 12. So 12 over 72, which is 1/6. So the probability is 1/6. In fact, the same as rolling any of the individual numbers on a third die. This is a more complicated example using conditional probability and considering a case where the outcomes are not all equally likely. In the next video, which will be the last one, we're going to consider a few additional examples of probability. There won't be any new concepts, but just additional examples.